According to Lesson 1, the curing process is a crucial stage in producing fiber-reinforced composites. This process involves applying heat and pressure to the composite material. During the curing process, first the resin exhibits a viscous flow state. With the application of heat and temperature, the resin gradually gains stiffness while also experiences shrinkage. This indicates that the composite is in the curing process. Finally, the composite's elastic modulus stabilizes. To gain a clear understanding, consider the changes in the resin stiffness during the curing process in the figure. Initially, the stiffness is quite low until the resin reaches the gel point. Afterward, it gradually increases until reaching the glass point. Finally, the composite achieves a fully cured stiffness and it is ready to be used in various industries. Now you should understand the importance of carefully conducting the curing process to create high-quality composites. Note that an incorrect curing process may result in excessive residual stresses within laminate layers. Hence, utilizing numerical models as cost-effective methods is a way to design a high-quality curing process for laminates, a topic we have covered in this lesson. However, two challenges arise. First, during curing, we have two heat sources, the applied temperature and the internal heat generated due to chemical reactions. Analyzing heat distribution requires considering both effects, which is complex and necessitates advanced models. This topic is covered completely in Lesson 1. The second challenge is development of a numerical model that considers the effects of thermal expansion, chemical shrinkage, and the mechanical strains in a problem together. We will explore this topic in the current lesson. Similar to the first lesson, we will use the heat conduction and the cure kinetics equations together to analyze the heat distribution in the composite. However, this time we need to go further by including the mechanical aspect to develop a thermo-chemo-mechanical model. You might wonder how we do this. It is simple. Let us describe. In the thermo-chemo-mechanical model, heat distribution depends on both the applied temperature and the internally generated heat. Moreover, the heat distribution and the chemical shrinkage contribute to introducing non-mechanical strains in the model. In such a model, non-mechanical strains rely on the curing level, applied temperature, and internally released heat. Additionally, two critical factors, including the degree of cure and temperature, affect the stress distribution. As a result, the mechanical fields rely on both the temperature distribution and the chemical reactions. So, we need to perform a thermo-chemo-mechanical analysis.